In this video, we're going to look to see how to find the length of a polar curve. So, just like the length of every length of a curve function we've seen, this formula is based on distance formula or Pythagorean theorem, but it's a little bit different than parametric or just Cartesian functions. And so it will be the length is equal to the integral from alpha to beta, because we are going to consider two theta values, of the square root of r of theta squared plus dr d theta squared all d theta. Now you can relatively easily prove this, so the proof can come from the fact that we know that x in terms of theta, the Cartesian x, will be r of theta cosine of theta, y will be r of theta sine of theta, and we know and understand the length of a parametric equation as the integral from a to b of the square root of, in this case, dx d theta squared plus dy d theta squared all d theta. So this is a way to actually prove it. It doesn't do a great job of explaining why it works, but algebraically you can go through, and when you take care of the fact that sine squared plus cosine squared equals 1, this will fall out of it. But a little better explanation as to why, so this will explain more of why. And recall that if we have a circle, that means that dr d theta was equal to 0, and I look for a small arc, so that angle there being theta, the arc length will equal theta over 2 pi multiplied by the whole circumference, because we have theta out of the whole 2 pi. Well, the circumference is 2 pi r, so theta over 2 pi multiplied by 2 pi r, and the 2 pi's cancel, and we get theta times r. And you see, if this is 0, then the square root of r squared is just the absolute value of r, and we have r times d theta when I make this exceptionally small. But in most of our cases, if dr d theta is 0, we'll have a circle, but so we don't care about that so much. We could use geometry. We care about when we have a changing function. And so if we have a function that's doing something interesting, like let's say this function, when I look at a very small portion of it, since it's differentiable, it must be locally linear. And what happens is this. From any 2 points on here, we have the part that would be going along the circle, and that was found by doing r d theta. And then we have the part that's moving away from the circle, how far the sort of radius or distance from the center is changing, and that's where the dr comes in. And that's why we have this squared plus this squared. Those are the two parts of this triangle. And notice, unlike the previous formulas, these aren't vertical and horizontal. This one goes along the circumference of the circle wherever we are, and this one goes away from the origin. Let's look at two quick examples. So here's example 1. We want to find the length of this from theta equals pi to theta equals 6 pi. Now I could dive right in, but let me show graphically what's going on in this problem. So in this problem, sorry, that's the next example, theta over pi looks like this, a lovely sort of curly unit. It keeps on going. I stopped at 10 pi. Let me fix that so we see that it doesn't actually stop. So let's go all the way up to, let's see, 20 pi should be more than sufficient. Okay, so lovely spiral. But we only want the portion from pi to 6 pi. So if I start here, this is 0, pi over 2, pi. 3 pi over 2, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So we only want this portion of it. And so finding the length of this is actually pretty straightforward using our formula. So I need to find the length. It's going to be the integral. They have the starting and stopping theta values, pi to 6 pi, of the square root of r of theta squared, so theta divided by pi squared, plus dr d theta squared. Well, dr d theta is just the derivative with respect to theta of 1 over pi times theta, and so this is linear. That derivative is just 1 over pi. And I'm going to go to a calculator, and so if I go to my calculator, I can use x in place of theta to make my job easy. So math 9, the integral from, sorry, that's not good, the integral of the square root of x over pi quantity squared plus 1 over pi quantity squared. In this case, dx from pi to 6 pi. It might take a few seconds, not too long, 55.261. Okay, now just for your knowledge for these TI calculators, if you would like to have it give you thetas instead of x's, the easiest way is just to change the mode to polar. And now this button will give you x or thetas. Okay, it doesn't matter, you have a variable. I can change out all the variables using sort of x substitution, but yeah. Alright. Second example, find the length of one petal of this graph. Now, like the problem we had for area, there are two good methods to solving this problem. First, let's see graphically what is going on. So, get rid of these. The graph of 2 cosine 6 theta is this. Let me zoom in a little bit. Okay, and if I want one petal, well, here is one petal of this. Now I'll come back to this when I show my second method to explain why I highlighted this petal, but any petal is the same. They're all, it's symmetric over rotation, actually 12 times. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 petals here. So the first option is to just find the length of the whole curve, and so the length of the entire curve will be, since I have a 6 theta, an even number of theta, it goes from 0 to 2 pi. If I had an odd theta, like a 5 or a 7 theta, it would just be 0 to pi. And I do the square root of r of theta squared, so 2 cosine 6 theta squared, plus dr d theta squared, which is going to be negative 12 sine 6 theta. Negative 12 because I need to do chain rule with this 6 theta. Sine and negative because the derivative of cosine is negative sine, and this is squared d theta. So I'll go to the calculator and do that. So the integral of the square root of 2 cosine 6 theta, I still have theta on, okay, lovely, squared, plus negative 12 sine 6 theta squared d theta from 0 to 2 pi. As this is running, just a few reminders. The square root and these squareds don't cancel because there's this sum between. I can't bring this out as a minus because this is all squared. I don't need to do this by hand. I usually just like to write out the correct expression and then put it into the calculator, because actually for this example, expanding any of this stuff out doesn't help save the calculator time. It only gives you more opportunities to make mistakes. I mean, I guess you might forget that a negative squared is positive. So you might do like 12 squared is 24. Just dumb mistakes that could show up. Whereas if I know this is right, I'll put in the calculator. It's still thinking because of the way that this graph works. I'll go and explain one reason why it's taking so long. The reason it's taking so long is a lot of this very steep work right here, where it has to split up the integral into smaller and smaller pieces to well accommodate how quickly this is coming in and out. And it's just taking a little bit of time. So I guess that's in addition to cosine not being a simple and sine not being simple things to evaluate. So I guess I'll let this run. It should be done very shortly. I'll show why the other method that I choose. So I can do this, and once I get that, divide it by the 12 petals to get my, let me move that down so I have space to write that, divide by the 12 petals to get my final answer. Or I can do this method where I'll find out where the start and stop of a single petal is, and that's going to be by setting r of theta equal to 0, because one of these petals, they start at the origin and come out and end at the origin, and that's where the r, the distance from the origin, is 0. Now, getting back into there, so that's where 2 cosine of 6 theta equals 0. That means the cosine of 6 theta is equal to 0. And that happens where 6 theta is equal to pi over 2, 3 pi over 2, and so forth and so on. I don't need more than 2 because this will be a single petal. To solve for theta, I divide by 6, and I get theta equals pi over 12, or 3 pi over 12, which is pi over 4. And this final answer should be the same as the integral from pi over 12 to pi over 4 of the same integrand, 2 cosine 6 theta squared plus negative 12 sine 6 theta squared d theta. All right, let me go back to the calculator. I should have this answer, or sorry, this answer. So the calculator has finally come up with 49.800. And I will divide that by 12. And I'm going to keep all of the calculator. I'm not going to retype 49.800. I'm going to keep all of these decimals so I don't get round off error to the third decimal. And I get 4.150 as the approximate length of one petal of this. Now let me show that these do actually end up being the same. I will skip the time it takes for the calculator to get here, but I could, so let me go back second entry. So instead of going from 0 to 2 pi and then dividing by 12, let me go from pi over 12 up to pi over 4. And if it doesn't finish by the time I'm saying this sentence, I will skip the time and we'll see what happens, what the answer is. Oh, okay, that was pretty quick. You can see, same solution. Alright, I hope that helped out. Feel free to comment below if you have any questions.